Welcome everyone, and thank you for joining me today. I'm excited to introduce our presentation on piping engineering. On this first slide, we'll briefly overview what piping engineering entails. We'll look at its scope, including design, construction, and maintenance of pipelines that carry oil, gas, steam, water, and chemicals between different units. We'll also touch on the main focus areas such as design, selection, installation, testing, and operations and maintenance. Additionally, we'll explore the industries we serve like refineries, petrochemical plants, power plants, and desalination facilities. Finally, we'll mention some key standards, including ASME B31.3 for process piping, ASME B31.1 for power piping, and API 570 for piping inspection. So let's get started and dive into the world of piping engineering. Let's take a closer look at piping drawings, which are fundamental to our design process. Two key drawings guide all our work. First, the process flow diagram, or PFD, which provides an overview of the entire process and the main equipment involved. Think of it as the big picture. Second, we have the piping and instrumentation diagram, or P and ID. This is more detailed, showing the specific valves, instruments, line specifications, and control systems. It's like the detailed map that ensures everything functions properly. Now, to keep these diagrams consistent and clear, we follow symbol standards like ISA 5.1 and ISO 10628. These standards help everyone understand the drawings easily, no matter who's reading them. Visually, I like to think of the PFD and P and ID side by side, with arrows indicating the flow of materials and control signals. You'll also notice specific valve symbols that are standardized, making it easier to interpret the diagrams quickly. Overall, these drawings are essential tools that connect the overall process design with the detailed control and piping specifics, keeping our projects organized and on track. Let's start by looking at the basics of pipeline design. It all begins with understanding the required flow, pressure, and temperature for your system. These parameters are essential because they determine the size and specifications of your pipeline. Now, to figure out the flow rate, we use this fundamental formula. Q equals A times V here. Q is the flow rate, A is the cross-sectional area of the pipe, and V is the velocity of the fluid moving through it. When we expand that formula, it looks like this. Q equals pi times d squared divided by 4 times V. This helps us calculate the volume of fluid passing through the pipe at a given velocity. For example, if we consider a 6-inch pipe, which is about 0.152 meters, and the fluid velocity is 3 meters per second, then the flow rate Q comes out to approximately 0.0545 cubic meters per second. That's roughly 195 cubic meters per hour. It's important to remember that we need to stay within certain velocity limits to prevent issues like erosion or noise. Generally, for liquids, we aim for velocities between 1 and 3 meters per second. For gases, it's typically 10 to 20 meters per second, and for steam, 25 to 35 meters per second. Finally, when designing pipelines, we also need to reference the relevant codes. One key standard is ASME B31.3, Clause 301, which covers design pressure and temperature requirements. This ensures our design is both safe and compliant with industry standards. Let's talk about pressure drop and pump head. Every meter of pipe you have in a system adds some friction loss, which means the fluid encounters resistance as it flows. To estimate this, we use a simple formula. Delta equals 10.2 times the product of the pipe length and the square of the velocity divided by the pipe diameter. This gives us an approximate pressure loss in kilopascals. For example, if you have a 100-meter-long pipe with a diameter of 0.15 meters and the fluid is flowing at 3 meters per second, the pressure drop, or delta, would be around 61 kilopascals. This helps us quantify the resistance the pump needs to overcome. Now, to find the pump head, which is essentially how high the pump can lift the fluid against this pressure, we use the formula. Pump head equals the pressure drop times 10.2 divided by the fluid density. In this case, That results in about 6.2 meters of wall head. It's also important to remember that there are standards and codes guiding these calculations. For pressure loss, we refer to ASME B31.3, and for pump design, we look at API 610. These standards ensure we're designing safe and efficient systems that meet industry requirements. Now, let's talk about material selection, which is a critical step in designing a reliable piping system. When choosing materials, we need to consider factors like pressure, temperature, and the type of fluid that will flow through the pipes. For example, carbon steel, such as ASTM A106 or A53, is typically used for transporting oil and steam because it can handle high pressures and temperatures. If we're dealing with corrosive fluids, stainless steel, like ASTM A312 or A409, is the better choice due to its resistance to corrosion. For applications involving high temperatures, alloy steel, specifically ASTM A335, is preferred because it maintains strength and stability under extreme heat. And when the service involves cryogenic temperatures, low-temperature carbon steel, like ASTM A333, is ideal because it remains ductile and reliable at very low temperatures. Moving on to fittings and flanges, we follow established standards, such as ASME B16.5 for flanges and ASME B16.9 for fittings, to ensure compatibility and safety across the system. To give you a visual idea, imagine a color-coded pipe rack, gray for carbon steel, silver for stainless steel, and gold for alloy steel. This helps quickly identify materials at a glance and enhances safety and maintenance efficiency. Overall, selecting the right materials based on these factors ensures the integrity and longevity of the piping system, which ties back to our overall goal of designing safe, efficient, and reliable infrastructure. Let's talk about pipeline stress and expansion. As pipes heat up, they tend to expand. To accommodate this, we incorporate flexibility into the system using features like loops, bends, or expansion joints. These elements help manage the movement caused by temperature changes. Now, to quantify this expansion, there's a simple formula. Deltal equals alpha times L times deltat. Here, deltal is the amount the pipe expands, alpha is the coefficient of thermal expansion, L is the original length, and deltat is the temperature change. For example, if alpha is 12 times 10 to the minus 6 per degree Celsius, the pipe is 30 meters long, and the temperature increases by 100 degrees Celsius, then the expansion deltal would be about 36 millimeters. It's also important to note that anchors and guides are used to control and direct this movement, ensuring the pipe stays in the right position and doesn't cause stress or damage. When designing these systems, we follow codes like ASME B31.3 and B30.11, especially for flexibility analysis. Visually, imagine a piping system with an expansion loop and a spring support. These features allow the pipe to move safely as it expands and contracts. Understanding and managing pipe expansion is crucial for the durability and safety of the entire system, and it ties directly into the overall theme of reliable pipeline design. Let's take a closer look at slide 7, which focuses on valves and instruments. Valves play a crucial role in controlling the flow of fluids within a system, while instruments are used to monitor key parameters like pressure and temperature to ensure everything runs smoothly. When it comes to types of valves, you'll commonly encounter gate, globe, ball, check, and control valves. Each of these has specific applications and advantages depending on the process requirements. Valves are rated according to standards like the ASME classes, which typically range from 150 to 2500. Higher classes mean the valve can handle higher pressures. Understanding flow through a valve is also important, and there's a standard formula. Q equals CV times the square root of delta P divided by specific gravity. For example, if we have a CV of 80 and a pressure difference of 1 bar, the flow rate Q would be approximately 80 gallons per minute. Standards such as API 600, 602, 6D, and ISA 5.1 guide the design and manufacturing of these valves to ensure safety and reliability. To give you a visual idea, imagine a 3D assembly of a valve complete with a pressure indicator and a control loop bubble. This helps illustrate how valves and instruments work together within an operational system. Overall, understanding these components is essential because they enable precise control and monitoring, which are key to safe and efficient plant operation. All right, let's walk through the key points for the installation and welding process before the hydro test. First, it's crucial to verify the drawing and alignment of the piping system. Ensuring everything is correctly aligned and matches the design drawings helps prevent issues later on. Next, we move on to welding the joints according to ASME Section IX, which involves following the WPS, or Welding Procedure Specification, and PQR, the Procedure Qualification Record. These standards ensure our welds meet quality and safety criteria. After welding, performing non-destructive testing, or NDT, is essential. This includes radiographic testing, RT, ultrasonic testing, UT, penetrant testing, PT, and magnetic particle testing, MT. These tests help us detect any defects or flaws that could compromise the integrity of the welds. Once the welds pass inspection, we clean the surfaces thoroughly, apply coatings, and insulate as needed. Proper cleaning and coating help prevent corrosion, while insulation maintains temperature control. Remember, color coding is important for service identification: blue for water, red for steam, and yellow for gas. It's a simple way to keep track of different lines and ensure safety. We also follow specific codes, primarily ASME B31.3 for process piping and AWS D11 for structural welds. These codes guide our entire process to ensure compliance and safety. Finally, visually, you'll see weld joint diagrams with NDT points marked, highlighting where inspections are performed. This visual helps us understand the critical inspection spots and maintain quality throughout. So, in summary, verifying drawings, proper welding, rigorous testing, and clear identification all come together to ensure a reliable, safe system ready for hydro testing. Now that we've completed the installation, it's essential to move on to the testing and commissioning phase. First, we'll perform a hydrostatic test, which involves pressurizing the system to 1.5 times the design pressure. This helps us ensure the integrity and strength of the piping under stress. Next, we conduct a pneumatic test using air or nitrogen, but this time at 1.1 times the design pressure, to check for leaks and overall system tightness without risking damage. After these pressure tests, we need to flush and clean the system thoroughly until the fluid runs clear. This step is crucial to remove any debris or contaminants that could affect operation. Then, we calibrate all pressure and flow instruments to ensure they provide accurate readings during operation. It's also important to note that these procedures are guided by standards like ASME B31.3, API 598 for valve testing, and ISO 9001 for quality assurance and quality control. And as you can see in the visual, we often use a schematic setup with a pump and pressure gauge during testing to monitor the system closely and ensure everything functions correctly. This phase is vital to confirm that the entire system is safe, reliable, and ready for operational use. Now, let's talk about operation and maintenance, which is crucial for keeping our system both safe and efficient over its lifespan. The main goal here is to perform regular checks to catch any issues early and ensure everything runs smoothly. This includes inspecting for leaks, checking valve operations, cleaning strainers, and calibrating gauges. These routine checks are essential for maintaining system integrity and safety. It's also important to record all this data meticulously in the operations and maintenance manual, including the scheduled inspection intervals. This way, we have a clear history of maintenance activities, which helps us plan future checks and ensure compliance with industry standards. Speaking of standards, we follow API 570 guidelines for inspections, which provides a comprehensive framework for piping inspection and integrity management. Additionally, ISO 14224 guides us on maintaining detailed maintenance records, ensuring transparency and consistency across our operations. Visually, imagine a digital dashboard that displays upcoming maintenance tasks and inspection schedules. This helps us stay organized and proactive. By adhering to these practices, we can ensure our system remains safe, reliable, and compliant, supporting the overall success of our project.